with our class. So yeah, I sent an email today to Canvas. So we have a room reserved in Newark, room 302. That room can have broadcast, but this room can't have broadcast, which is weird because we have all the cameras and everything. So I don't know why we can't do this, but I will continue broadcasting through WebEx, which is not ideal, but it's better than nothing. And I will post the recordings on the modules page once they are available. But if you can't, please try to attend the class in person because that's more, can have better interaction. Okay, so I posted this morning the first assignment. Now I have to let everybody in one by one. Oof. Okay, it's a short assignment, but it gets you ready for to do the Keras and building simple neural networks, similar to what we are doing in class right now. And then a couple of theoretical questions about maximum likelihood, just to make sure that everybody at least theoretically understand what's going on. Okay, and then in the modules page, go to the student view so that make sure that what you can see, because some things I can see what I. Okay, so this is first module, which we are done. I will just go over these two scripts today. And then the second topic, so we are going to I'm going to talk about backpropagation, which is the main engine. So we will see what that is all about. I mean, it's basically a tool for differentiation in an automatic way, but you have to understand that the functions we are dealing with have hundreds of thousands of variables. So it can't just, and they're very, very complicated. So when you want to minimize, you need to take your gradient or derivatives, and that itself is a process. It needs a good algorithm. So we'll talk about this maybe today and then part of the next week, and then we'll go on to talk about some other issues with respect to neural networks, the main parts of a typical neural networks, like how you initialize, what are the activation functions, and regularization, and so on and so forth, a whole bunch of stuff. So it will take us a few weeks to go through those things, and then we're going to go into convolutional neural networks that are perfect mostly for image processing and pictures processing and so on, and then recurrent, and later we're going to talk about recurrent networks, and then attention networks, transformation mechanism, and so on, and then we're going to go to autoencoders and these GANs and deepfake stuff and so on and so forth. Okay, so that's that. So let me also, I have posted, these are, so I will try to have both single standing Python scripts like this, but also I will post, I will put them together at the end of the module and put them into a Python notebook. The Python notebook, I strongly encourage you, if you don't know what it is or you haven't installed it, you go ahead and install that. It is very useful. It has very nice, because you can have code and you can have text. Very complicated. It's like PDFs and math and etc., and then code again and so on. So it's very nice, and it opens inside a web browser, which I'm not sure if that's very nice. I mean, the web browsers are heavy duty software. So anyway, but that's how they design it. The thing I don't like about Python notebooks is that you cannot load a cell from some other notebook and put it in there. Now you can, but you have to do a lot of hack. I mean, that's a learning curve. It's not a simple process. You have to download and install something and complicate it. So if you have a piece of code that you use a lot, you have to basically copy and paste it 1,000 times. That's annoying. But other than that, it's a good interface. So I will try to use this interface as well. Okay, so I don't have a Python notebook. I actually prepared this, so I will post it after the class. Okay. What else I was going to say? Okay, so yeah, let's go. So the next homework is due on basically Thursday, from a week from tomorrow at night. So try to be on time. I still don't know who our teaching assistant is. I will check and I will post his or her information at the top page. I will post it somewhere in here. So yeah, over here somewhere. So as soon as I know exactly who that is. Okay. So this is Python. Let me see. Yeah. So I think we did this last week. Is this small? Is it better? Yeah. I can look at this. There's a way to get rid of this. What was it? This maybe? No. That no. I don't know. I don't know how to get rid of this. Huh? Yeah, but it doesn't go further. This is it. It refuses to go any further. Anyway, so last week, there are, as I mentioned, there are some famous data sets that everybody works on, and they're available, and they are available in Keras. You don't have to download the file or anything. Once you load Keras or TensorFlow, these data sets are there. So one of them is this MNIST. NIST is, I think I mentioned this last week, but NIST is basically National Institute of Standards in Washington. It's a federal institution which deals with standards. But anyway, these are pictures of basically people in post office. When people wrote letters and they wrote zip codes, they took pictures of zip codes, the digits, handwritten digits, and they turned them in basically 28 by 28 grayscale pictures where every pixel is a number between 0 to 255, and which is basically the intensity of gray. So 250, it's kind of the reverse of what it's supposed to be. It depends on how you want to show it. But you can have 255 as the blackest of the black, and the 0 as the whitest of the white, and then everything in between. But those of you who remember in computer science, it's actually the other way around. I mean, the black is supposed to be 0 and the white is supposed. But you can read this mostly. These pictures are the reverse drawn. Doesn't matter. And so there are about 60,000 of them, and then there's another 10,000 that are considered as a test set. So it's very simple. You see, this is where is it? Yeah. So you simply import from keras.datasets. But where did I? Yeah. From the keras.datasets you import it. And then MNIST is one of them. There's a whole bunch of other stuff that as we go. And you can explore. You can actually say keras and datasets and then explore and see what kind of other datasets are there. Anyway, so So these are important from Keras. I will talk today about TensorFlow, what TensorFlow is. But right now, think of TensorFlow as something. I assume most of you know what NumPy is for Python. That's a numerical library that does all these, mathematical stuff plus matrices and vectors. So that's NumPy. TensorFlow is essentially like NumPy. Okay. Now, why are they duplicating? Is because they have redesigned the whole thing so that it works on GPUs, on parallel processors. Okay, so that's the difference. So TensorFlow is like NumPy with slight difference. Most of the names are the same, but there are slight differences here and there. So we have to be careful with that. So that's one thing. Plus, TensorFlow also has this automatic differentiation algorithm, which we'll discuss, this backpropagation technique, which we will discuss hopefully today or maybe next time. And so that's the basis. And then it has a lot of other stuff, data processing and so on. Now, Keras, so you can think of TensorFlow as a lower level library. Like you have to if you have a formula or something, you have to write it down. Now, Keras is another library on top of TensorFlow. So basically, it's designed so that you build your neural networks. If you know the architecture in your head or you have drawn it in a piece of paper, you say, okay, I want to have this layer with this many variables and then another layer with that many variables, et cetera, et cetera. You draw something, and then it's, as we'll see, it's as easy as just basically translating that, what you said, essentially word for word using the Keras technique to design your neural network. So it's very, very handy. With a few lines of code, you can really construct extremely sophisticated and complicated models. So we will see. So I did this last time, just to review. So right now, we are looking at what is called the sequential interface. Okay, the sequential interface is yeah, so the sequential interface, as I probably have said before, looks like this. So basically, here are your inputs. You have a bunch of inputs, okay? And then remember, we go through some matrix and then some activation function, nonlinear activation function, okay? And then that's basically sequential. I mean, one layer after another, after a layer, after a layer, okay? So here is another, nonlinear, and so on. And you do it as many as you want. And then at the end, depends on what you're trying to do. If you have just one Y, like a regression, then there is only one Y. If you have a classification problem where there are, let's say, 10 classes, then there will be 10 Ys. Okay, so it depends on what it is. So that's basically the output. So it's called sequential because one after another, after another, after another. Now, is there anything other than sequential? Yes, for this course, probably 2/3 of the course, maybe 3/4 of the course, we are going to work with sequential models of various forms. But there are other types of architecture. So for example, you may decide, I want to have my X to go to here, but I want to have X go over there too. Okay, or you may have a situation where here are your X's. So here are your X's, your inputs, and then you may have some layer here, another layer here, and then they may go to another layer. So you can have more complicated, and then this layer's output goes there. You can have more complicated things. These are not sequential. You can have these kinds of architectures, okay? So the sequential interface doesn't work very well with this, or as far as I know, it doesn't work at all. So it's only designed for this kind of thing. Okay, which is fine, which is about 2/3 or 3/4 of what we want to do. It's very easy. It's very simple, intuitive, but limited. Okay, so wrong place. Okay, so basically you have to import the models and the layers. By the way, I don't know if you have the same problems I have. Depending on what version and so on you use, I get all sorts of errors. Like when I run it for the first time, it's an error, but I have to run it the second time, then it's fine. I'm not quite sure, and every time that is updated, something else happens. So be patient, because these people, the Keras and TensorFlow is designed by Google, and these people don't care much about backward compatibility, and they just want to do whatever ideas, they dump it in and they release the code. It's always, everything is beta. So just keep that in mind. So okay, so then you will create something called network, which is a model.sequential. Okay, so basically the network, you're defining your network, and essentially what you do, the first layer, you have to say what the input, the first layer needs to know the input. So you are giving the input shape here. Okay, so since I know my inputs are 28 by 28 pictures, so typically neural network work with just one list of data. So either you can use a 28 by 28, and then there is a layer called flatten, you can use that, or you can turn that into a, the 28 by 28 matrix can be turned into a 28 times 28 long vector, 784 long vector. So that's what we're doing here. Activation, I mentioned that's the nonlinear part. So you multiply by WX, and then you apply a nonlinear. Now, it doesn't, we will talk about this extensively about activation. For now, have something in mind, some nonlinear function. Now, sigmoid e to the x over 1 plus e to the x was a very popular activation. There are some issues with that. ReLU is a very simple function. It's basically is equal to 0 if x is less than 0, and it's equal to x if x is larger than 0. So it still is a nonlinear, but it's the simplest nonlinear. It's like a line, 0, and then just x. And what is amazing is that with the combination of linear transformation of the input and applying even something like a ReLU function, something like that, you can mimic any complicated function. Now that's really amazing, but that's true. So anyway, we are using ReLU as our activation. You could use sigmoid or any other thing. And then here I decided to choose 3 layers. So the first layer takes the input, 784 dimensional input, and then the next layer I choose to have 512. Now why? Really, there is no, I mean, there are some reasons, but essentially it's trial and error. Okay, so if it works, then it works. So that's the part that is not really an art. We don't know exactly what's going on, why this number works, but that number doesn't work, and so on. So basically, we are downgrading. 784 variables are mapped into 512, and then the next layers, it doesn't need anything because it knows that the previous guy had 512. So you only basically specify what the output is. The input was the previous. The input is the output of the previous layer. So here, the input to the first layer is 28 by 28. The output is 512 Zs. Okay, so that means that Z is equal to W to be found times phi, that activation, and output is 512. You take that 512 and feed it to the next layer. So again, 512 next layer, and the output, this is the output, is also 512. And again, is another bunch of W's, and then you multiply that by phi, which is in this case ReLU. So you can have different kinds of activations in different layers if you want to usually, unless there is no good reason for it, we use the same activation, but it doesn't matter. And then, so here I have two middle layers, and then I'm the last output. Then I'm going to the end. The end, so this is a classification problem, right? The output could be 10 different things. You have to decide whether it's the picture of a 0 or a 1 or a 2, etc. So the output of that is 10. And the activation here, now it has to use that softmax function that I mentioned last time, that, for the logistic regression. So this is essentially a logistic regression, except that it's not linear. It's this complicated composition of functions. So that's why the activation here is the softmax function. Okay, so as you practice, you'll realize there is a whole menu of activations available. So you should just know that there is something called softmax and something called logistic and ReLU and this and that. But as we will see later, it allows you to write your own, all of these pieces can be engineered, okay? So if there is some weird activation that you have in mind, you want to test and it's not available, there are ways to write your own activation function and add it to the system. Okay, anyway, so that's it basically. So this my neural network here for the digits, which uses logistic regression with softmax function, but not linear logistic. This neural network logistic has 784 pixels coming in, a 512 layer in the middle, another 512 layer in the middle, and then at the end 10 output telling you the probabilities of each class. And then you have to compile it. So you put them together. It's compiling is basically you now put this network together. You have to tell what kind of optimization algorithm it has to use. Right now, keep it with SGD. SGD is actually the weakest one. It's not very good, but I mean, it's the most important one because everything else is based on that. But this is just plain vanilla SGD, but that's fine for this problem. The loss function the loss function is basically logarithm of the softmax function. I mean, we saw that. It's the likelihood function. It's in the notes. I discussed it last time. So that actually is called categorical cross entropy. And then the metric, what is it that you're trying to follow? So there are two things here that is trying to optimize. Well, I mean, they're trying to follow. The thing that is optimizing is the likelihood function, which is the log of the probabilities, each probability designed by that, specified by that softmax function. So that's what is actually trying to minimize or maximize. Okay, and in order to choose W's such that that thing is maximized. But it also looks at accuracy. Accuracy means, okay, I have now some guess for W's. Using these W's, let me see how I can predict the training set on the training set. Okay, and then maybe the accuracy is the percentage of correct guesses. Okay, so it is not optimizing this, but it is keeping track of it. Okay. Okay, so that's nothing. So far, we're just specifying our neural network. No action has been taken. So now, as you can see, I have training images. I reshape it to 28 by 28. So this is actually a 3D. So training images, originally when I read it, when I read it here, load data, this train image at the beginning was a 3-dimensional, it's kind of like a box. It's a 28 by 28 picture, but there are 60,000 of them. So it's kind of like 60,000 pictures. So think of it that way, okay? Now we need to turn it into 2-dimensional. So the 28 by 28 is gonna be turned into a 784 dimensional 1 dimension, but then The 60,000 is each instant. So that's what we are doing here. We are reshaping the image to 60,000 by 784. Okay. Very, very important scaling. Those of you who have taken machine learning courses before, the one that I taught last semester, we emphasize it is absolutely essential that the data fed into a neural network to be scaled. What does the scaling mean? So just a quick reminder. So in general, your data are objects or measurable objects, somebody's height, somebody's weight, I don't know, the intensity of light, etc., etc. Okay? Now, when you measure an object, you can change the units of measurement. Okay? So I can have a distance could be in centimeters or distance could be in miles. I mean, there's going to be gigantic numbers multiplied. If you mix up these kinds of numbers into a most learning algorithms, not all, there are a few that are immune to this, but most learning algorithms, if you change scale, they give you different answer. So if you change, for example, if you have a money price in dollars, and then you say, okay, I'm going to go to Japan, I'm going to change the dollar column to yen. The same data, it's just multiplied by the exchange rate. Then you retrain, and suddenly completely different numbers. So they are very sensitive. Neural networks are 100 times more sensitive than any other thing. So to alleviate this problem, we have to turn our items into unitless numbers. So it means that if something is divided dollar, you can divide by, for example, the largest number. So it's dollar divided by dollar means unitless. So then it doesn't matter whether it's in yen or whatever. If the largest dollar amount was $10,000, you divide by 10,000. If it's in yen, it would be 1,000,000 yen. You divide by 1,000,000. When you divide, all the numbers become the same. So it's absolutely essential to scale the data. Now, in the case of images, in this case, we are lucky because we know that the images are between the intensities of the pixels. Also, by the way, it's especially in neural networks, it's better to scale it to either 0, 1 or -1, depending on the situation. Okay, so wherever the absolute value of the numbers should be kept between 0 and 1. So in this case, we are lucky because the images are the intensities of the grayscale from 0 to 255. So we know that the largest number is 255. So we just simply divide by 255. So scaling here is very simple. You have to also make sure that the test image is the same way, I do the same, and then scaling the same way. Okay. I'll come back to this two categorical later. Well, actually, why not? So the Y, so these are the X, and then it says this is the picture of something, and then it says it's actually a picture of 0. So on the Y column, you have some number like 0, 1, 2, 3, but remember, this is not a number, this is a symbol. It says this is the picture of a 0, so it's not a numerical. But Keras doesn't know that, so you have to turn it into what is called categorical. Categorical means that it turns into the number 0 or the number 1 into a symbol 0, so that it knows it's a classification problem. Okay, and all is done. Then this is where the action actually takes place. So the fit, so the network, so I defined the networks, the layers, etc. I compiled it. By compiling it, I said what kind of optimization do you use, what kind of loss function you use, etc., etc. So all is now designed, but nothing has happened yet. In order for me to something happen, I invoke the fit function on the network object, and then I have to feed it the data. Otherwise, what is it there? So the data is the training images, and then the training labels. So these are the X's basically, and this is the Y. Okay, so the X and the Y. Now, don't worry too much about the epochs and the batch size. We'll discuss this later. For now, just keep this as it is. And then that's it. So this fit object starts optimizing. Okay, and I will discuss this shortly, but basically optimization problem, you have a function f of several x's, several millions or hundreds of thousands in this case. And you start from some guess, and then you're supposed to go to a direction that reduces the value of the function. I keep saying reduces, but your mind says, but this is maximum likelihood. But maximization and minimization are the same thing. You just put a minus in front of it, it becomes, if it's a maximization, put a minus in front of it, it becomes minimization. So I'm going to talk in language of minimization, but keep in mind that it could also mean maximum. It's the same thing, basically. So anyway, you have to find a direction. And the directions are basically involve computing the derivatives. And that's where the backpropagation and stuff comes. I'll talk about that. But anyway, that's what this fit function does. All the action of learning happens with the fit function. Once the fit is done, that means it finds in its mind the best W's. So those W's are now that we know what those W's are, so we know that if I give an X, output comes the probability that this picture is a 0 or a 1 or a 2 or a 3. If I've done a good job, it's going to give me a very good result. If I've done a bad job, it's going to give us a bad result. And then then the rest is basic. So here I'm predicting. So this I use the training set to train. Now I use the test set. Now the test set is another batch of values whose bunch of new pictures, and they're stating what picture of what they are, but they were not involved in training. They were set aside. And now that I've trained, I'm going to test it on these guys to see if it's doing a good job or not. So prediction. So there are two predict classes. There are two predict methods for the network object. One is predict, which gives you the probabilities. So when you give a picture, which is basically an array of 784, this is basically the pixels of some new image, and then you feed it to this guy, out comes a vector of size 10, which gives you the probabilities of, so it says, okay, I see this picture, the probability that 0 is probably very small, 1 is very small, 2 is maybe it's a picture of 5, then it goes probably of 5 is 90%, and so it outputs a vector of probabilities that it thinks. So that's what this predict does, okay? But sometimes you say, I don't care about probabilities, just tell me what it is. The Bayes decision rule says, pick the one with the largest probability. So you can do it yourself. I mean, you can just write you can take this predict, the output of this predict, and just pick the one that is the largest and announce that as the result. Or if you're lazy, you don't want to do that, there's something called predict classes. The predict classes outputs, this is a picture of a 0, this is a picture of a 1, which basically what it does under the hood is takes the one that has the highest probability. Okay, and then this stuff, then we are going to run these classification report and so on, confusion matrix, to decide how well it did on the test data. So here, basically, I have a loop that it goes through all the test data, and I think I've set it up here so that if it did a correct decision, it will just pass. But if it did not, then so we are going to look at only the errors. So let me run this. So you see, it gives me error at the first time. I don't know why. It says layers. Yeah, I don't know what layer is, but you have to do it the second time and it works. I don't understand this. But anyway, so this is basically, this is the optimization problem. It shows it. You can shut it off if it annoys you. But if you look at that, the loss function, that's the value of the maximum likelihood thingy. So it's, in this case, it's 1.12. The second one was, so it's getting better and better, 30.35 and so on. But there's also the accuracy. So it started with 75% accurate. So The partial W, that W gave us a 75% accuracy. The next, then we improved it. The next one is now 88%. The next one is now 90%, 91%, 91%, etc. Yeah, so this, I don't know why this, yeah, unplugged it. Okay, so we can see, you know, the value of the objective function starts going smaller and smaller, but not very fast. But the accuracy, it's not trying to optimize the accuracy at all. It's trying to just optimize that log likelihood function, okay? However, it's also keeping track of accuracy by partially created W's, uses those W's to predict the training set. It doesn't have anything to do with test set. It doesn't know about test set. And so at the end, we get to about 95% accuracy, 95.7 accuracy. Okay, so this precision recall F1 score will, at some point, I may have the patients to describe what these are, but what you want to know is basically this, the 96%, which is that, basically that. And then the confusion matrix. So each row is the label of the classification. So in this case, these are pictures of 0, 1, 2, 3 through 9. So the rows are 0, 1, 2, 3, 4, 9. The columns are also 0, 1, 4, 3, 4, 9. And then for each picture, it says what is the true value, that's the row. What is the predicted value, that's the column. Okay, and then over the 10,000, so the 10,000 test problems, you get the result. So you want the diagonal to be large because those are the correct predictions. It was a 0 and I predicted 0. It was a 5 and I predicted 5. The off diagonals are all incorrect. So for example, if you look at this 11 here, this is basically 0, 1, 2, 3, 4, 5. It was a 5, but it was predicted to be a 9. Predicted to be 8, I believe. Yeah, 9 is the last code. Okay, so 11 pictures were 5s, but they were predicted to be 9. Okay, so that's what this is. And then you can actually visualize this by, so you will see that the diagonals, so these are basically the numbers. So red areas means very small number and the blue areas means large numbers. So you want the diagonals to be not red and the off diagonals to be as red as possible. It's just the way I have, give the color map. Okay, and then we can go over some predictions. So here, this is the first one that it got it wrong, this picture. Its actual value is 5, but it predicted it to be 6. And here are the probabilities for each assigned to each value. So it says there is a 0 probability that this is a 0. The 0 probability is a 1, and so on. Maybe a 1% probability that it's a 4. It has 1% probability that it's a 5, and a 98 probability that it's a 6. So it was pretty sure that it was a 6, but it wasn't a 6. I mean, I don't know. I wouldn't blame it. Okay. Then you can do this bar chart is just these numbers, so that you can visualize how it is done. So you can just test. The loop goes over other ones. So here is another one. It predicted this to be 6. I don't know why, but it's actually a 4. And then here are the probabilities. Okay, and then if you're tired, you can just say no, and then it goes away. So any questions about this? To the code? Yeah, the time is 4 seconds, basically. Yeah, it's basically these are wall clock. I mean, there is a lot of stuff going on my laptop. You know, it depends on how much the operating system gives it to this code versus other things that is happening. The output is up, all these other garbage is up. So yeah, but yeah. Okay, so that's what we did last time, basically. So for sequential interface. Now I'm going to do exactly the same thing, but with a different. It's called the functional interface. So functional interface is basically you are taking a layer and applying it to another layer. So it's kind of like that's why it's called a functional interface. So here. Yeah, we do this stuff. So the layers from layers library, we have to create the input layer. So in the sequential, we didn't care. We just said the first layer, the second layer, and the very first one, we said what the input size is because we had to tell what the input size was. For the other ones, the output of the previous was the input of the next one. So, but here we have to have an input layer. Now flatten. Now, so let me just step back a little bit. The word layer, when we talk in class, in a theoretical thing, is what I just told you. That is, here is one set of outputs, then you apply a W, and then you apply a activation. That's the definition of layer that we use, you know, for our discussion. In Keras, the layer means a lot bigger, you know, because anything that can stick in between, even though it's basically auxiliary stuff, you know, the side stuff, they call those also layers. Okay, so one of them is flatten, for example. Flatten, as the name says, all it does, it takes a multi-dimensional tensor or array and turns it into one-dimensional. So in the lingo of Keras, that's also a layer. So if you have something coming in which is a multi-dimensional array, you can pass it to a flattened layer. The flattened layer doesn't do anything other than turning it into a one-dimensional line. So just keep in mind that the word layer in Keras is more expansive than what we want to do. So anyways, and then the type of layers, these kind of layers, I mentioned it last time, these kind of layers called dense layers. Dense layer basically means that the W array, you know, there is all these weights. They could be anything, okay? As opposed to, for instance, sparse arrays where you say, oh, these numbers, these parts are is all equal to 0, but only these are allowed to change. You know, you can do more complicated types of weights. You can put restrictions on weights. And we will see later, especially in convolutional networks, that's exactly what's going on. But right now, dense basically means that weight matrix that comes in each thing, it could be anything. You specify the dimensions, the input and the output, and then inside, anything goes. So that's what's called the dense layer, and that's what we have been using. Okay, so again, I'm import the data, training, etc. So it's split the data to training, etc. So I have an input layer, which is input shape 28 by, so here the shape is two-dimensional, 28 by 28, okay? Then I apply flatten. The flatten, see there's a parenthesis, so the functional interface, a layer type, the layer object, outputs itself, it creates a function, and that function is applied to another layer. That's basically says the output of this comes to the input as the input of this one. Okay, so so here I have a flattened layer. Doesn't do anything. It's just a flat. It just makes it one-dimensional. But if you look at the interface, the flattened layer is applied to the previous layer. Now that's why you have to give a name to these guys, okay? So that is important because it has to have some, I mean, you could write it in ugly form, like I could have written flatten of close parentheses, open parentheses, and then instead of input layer, I could have said input of shape, blah, blah, blah. And then you can, but it's a little bit ugly. Okay, so, okay, so then the output of this is F, I call it F1 for flattened. And then the next one is a dense layer. I have to give parameters. It has 512 output. The activation is ReLU, and it's applied to the output of this thing, which is F1. And then the next layer is a dense layer with 512 activation. So here, I don't know why I changed it to sigmoid. It doesn't matter really, but you have to give some kind of a nonlinear function. ReLU is better. We will see later why. Theoretically, they all have the same power, but there is some practical reasons that ReLU is better. But I don't know why I put sigmoid here. I just noticed it. But it could be sigmoid. Sigmoid is 1 over 1 plus e to the minus x. Okay, so that's that. Anyway, I applied that, but this also shows that you don't have to use the same activation for each layer. You can play, you can do whatever you want. And then finally, I have an output layer, which takes H2, the output of the previous guy. I apply to that, and its arguments has to have 10 out, because it has to say which one it is, and the activation has to be softmax. Here it's not. This is not a choice. We have to choose. I mean, because we want to have the output, we want to be the probabilities, and we are through the softmax function. We are creating the probability. Remember, softmax was e to the something over sum of e to the somethings, and added up to 1, and everything was between 0 and 1, so on. So this is kind of mandatory here, unless you have another way of capturing probabilities in a smooth fashion. Okay, and then the rest is the same. The network, now here, the rest, so the network is now a model with an input and an output. You have to say what's the beginning, what's the end. Through these process, what's in between is defined now. It knows it's the input layer, that's what I call here, is the beginning. It knows the output layer is the end. And then through this area, it knows how I got from input to the output. The advantage of this approach, it's a little bit more complicated, but the advantage is that if I have something like this, I can give this guy a name. I can give this guy a name, this guy another name. I can apply, through functional, I can apply it to that. Through functional, I apply it to that, and so on. So I can have a much more if I wish, I can have more complicated architecture than just the sequential one. Okay, so that's the advantage of the sequential, the advantage of the functional API. Okay, but the rest is basically the same. You have to compile. This time I'm using a different optimization. We will see what this is later. RMS prop. But the rest is the same. Categorical cross entropy, that's basically log likelihood function for the multi-variable, multi-output. Metrics accuracy. Do your scaling. Make sure to do the scaling. To turn things, the Y labels to categorical, fine. And then the network.fit, again, the same. That's where the action happens. You give the training test, training X's, training Y's, and then other stuff which we won't worry about it right now. So the output is called history, and then I can, so network, so here network.evaluate, basically what's happening here is that instead of predicting, so if you're predicting, you can get the solution. Sometimes I'm not interested in the solution. I just want to know how it performed. So here, that's what you do. You evaluate. You give it apply to test, and then the output is not what for each item how it did. It just puts them together, and then the test loss and the test accuracy, the average test loss is done. Okay, but at the end, I still have to do predict. Now, something funny is that when you are using this functional interface, there is no predict class. So if you want to know just what the answer is, you don't care about the probabilities, there is no predict class. That's kind of a weird, I don't know why they don't have it, but it doesn't matter. You have the predict, which gives you the probabilities. You can pick the one that is the largest if you want to do. Okay. So here I define, here I map. So you can see, this is what my predict class. I wrote my own predict class. So this predict prob gets the test images, and for each one, the output is a 10-dimensional vector of probabilities for each. Okay, I take that, I apply the argmax function. That means which argmax, remember, it looks at the, if you have a vector of size 10, for example, max looks at the largest one. Argmax says where that largest one is. So if the largest probability is under the 7th position, then it is predicting 6, because 0 to 6. Okay, so it will predicting 6. So that's what I'm picking up. And then through a map, through the Python map, I apply it through do this array, and then so that's, I generate my own predicted class. Okay, and then the rest is the same. I go through all the test labels, and if they are not equal, if they are error, I will go over it. So let me run this. Okay, again. Yeah, I don't know why. Usually it runs much faster. I don't know what's going on. Now, I will show you how many variables, how many parameters we have. It's not hard to estimate. So the first one is 784 gives 512. So this 784 times 512, the first set of W's for the first layer. Then the next layer is 512 by 512. So you add that. And then the third one is 512 times 10 for that last one. So you add these up. That's a lot of, so it's minimizing over all these W's. So the fact that it's only taking a few, like 6 seconds or so, it's still considered slow, but it's doing a lot of stuff. Now, notice here, the accuracies are 99%, almost 100%, but don't be fooled with this. That's on the training set, okay? So we have to see how well it does on the test set. And so this is the phenomenon called overfitting. It is possible that you have a model that does excellent on the training set, but when you apply it to the test set, then it's not so hot, it's not so good. So that's a phenomenon called overfitting the data. One of the weird things, so some of you maybe took my class last semester about machine learning, algorithmic machine learning. We talked about overfitting a lot in that class and how to guard and what a problem it was. One of the weird things about neural networks is that overfitting happens. They say live and say overfitting doesn't happen. It happens, but it seems to be far less an issue. So you can have unbelievably complicated models, which the whole idea of overfitting says don't have too complicated models, at least not too complicated with respect to your data set. But you can have unbelievably complicated models, and still overfitting is not as terrible as it would be, for example, if you're using some other like linear regression or logistic regression, simple logistic regression, and so on. So here you can see the test accuracy is 98%. but the last training appearance is almost 1. So it's not bad, but there's a tiny bit of gap. The training set is a little bit more accurate than the test set. So tiny bit of overfitting, like 1%. But you can see situations where like the training is like, I don't know, 95%, and then you run it on the test is like 60%. Then that's a disaster. That means that you are a really bad model. It's overfitted. We tend not to see that in neural networks, and that is actually a major open problem. People don't. There are many things about neural networks that people don't understand. It's just heuristic. Okay, it's not clear. Like even the simplest thing, like why theory says the one layer is good enough. We should be able to fit in anything complicated with just one layer. Just increase the z's. Okay. But in practice, multiple layers somehow capture complexities of the functions without really getting too big. This is not well understood. Okay, this is not well understood. It's very complicated. You need to know mathematics and all this functional analysis and so on. It's complicated. Anyway, so here are, what is this? This is so like it. I don't know. It predicted that this is a non. Well, I don't know what's going on. Something is wrong with my labeling here. Yeah, I mixed up something. Yeah, I have to fix this. I don't know what's going on. Yeah. Anyway, but it gives you the probabilities. These are wrong. I can see that these are wrong. I probably mixed up the indexing. I'll fix that. Okay, so everyone see the difference between the functional approach versus the sequential approach, right? Sequential is easier, but you will need functional sooner or later. So it's incumbent upon you to learn that approach. Okay, now just one more time. So say no. Okay. So there is another data set. The digits this data set is considered too easy. I mean, again, in the previous course in algorithmic machine learning, we used even silly methods like naive Bayes and so on. They gave like 85% accuracy or something. So it's considered too easy of a data set. So they came up with something called fashion MNIST, which is basically, the format is almost the same. It's a 28 by 28 picture, grade scale between 0 and 20 to 55 of a bunch of pictures, 10 categories. But these are pictures of clothing, like, a shoe, a sandal, a shirt, a coat, pants, and so on and so forth. And this is more challenging, okay? So here, I'm using exactly the same architecture, 512, 512, and 10. Okay, so it's the same. Let's see how it does. Somehow I feel like my computer is slower than last year. I hope I gave 20. Optimizer, okay. Where is the compile? Oh, where is the fit? Yeah, 20. Okay, fine. Yeah. So these are these MNIST and these fashion MNIST and so on, and a couple of other ones are color. If it is a color picture, then it would be actually a three-dimensional. The word tensor, I mean, tensor in mathematics, in linear algebra is more complicated, tensor algebra. But in the language of Google and these people, tensor basically means multi-dimensional array. So a color picture is, so a black and white picture is just an array, right? An array of pixel of grayscale. A color picture is three arrays. One captures intensities of blue, one intensity of green, and one intensity of red. And the combination of these gives you supposedly any color. So there are data sets that are kind of like this, but color, and they are even more complicated. So here you can see that the accuracy is coming to around 90+%. The same architecture. Okay, but the test accuracy is 89%. So the gap is a little bit bigger now, but almost 4%. Okay, and so it's still very good. You know, it's still not bad, but you can see. But it didn't. That exact same architecture did not, but retrained for this data. You have to retrain the same for this data. It didn't do as much as well. By the way, this you can also these numbers here, the loss and the accuracy as the training proceeds, you can capture it and plot it if you want. So over 20 passes, you can see that the loss function started larger and then it gets smaller and smaller, and then the accuracy started smaller and get large, better and better. So this is good. It's useful to put these two on the same thing, because the blue, the loss function, is the one that the algorithm is actually minimizing. But what you are really interested in is the accuracy, at least. But this is accuracy on the training set. But nonetheless, that's the one that you're interested in. So there are situations where you see, oh, the loss function is getting much better, but the accuracy is just flatlining. So it is, that can happen too. This kind of happens here a little bit. It very quickly went to mid-80s, and then it's kind of like flat here. Whereas here it's still going down. It's a good steep improvement. Okay, and then the same, you can see that the confusion matrix is not as impressive anymore. There's a lot of orange. The off diagonals are not quite red. There are a lot of errors and so on. And then let's just look at a couple few. So here, for example, well, I don't know what happened here. Anyway, this is supposed to be, what is it? Well, it predicted to be a sandal, but it's actually a sneaker. But I mean, I probably would make those mistakes too, so I don't know. Okay, but again, I don't know what happened. Oh, the range. I have to fix that. Okay. Okay, so I need to fix that. Also, I don't know why these are supposed to be vertical. I don't know what's going on. Anyway, so that's that. Any questions? So in the homework, I give you a simpler problem than this, but you have to generate the data. So basically, in the homework, we have a binary classification, not multiple, and we have concentric circles. Okay, a bunch of concentric, but then, you know, the middle part is blue, and then the next ring is orange, and then the other one is blue and orange and blue and orange, like that. Okay, so that's the pattern that we want to learn. Okay, and then you generate, I don't know, 10,000 points and figure out which ones are orange, which ones are blue. That would be your data set. And then you feed it, and then you're supposed to design a neural network. And I suggest to you that start with just one layer and a small number of variables to see how bad it is or how good it is, and then try to improve and improve, maybe by increasing the numbers in a layer, and then maybe then adding one more layer and so on, and try to see if you can get to about 95% plus accuracy. So so that's basically what you're supposed to do. Very, very simple. The loss function is supposed to be binary version of the categorical cross entropy. Okay, so that's the only difference. But there you just generate the data yourself rather than loading it from somewhere else. Okay. So that kind of concludes our first topic, the introductory material. Yeah. For what? No, it's not really required. There are, for some situations, there is a good reason to have it a power of 2 because of how it's represented in the computer and so on, and doesn't have overflows. But no, it's not really necessary. You can play, especially since you have only 2 variables there. Like you have, it's a 2-dimensional picture, so there's only x1 and x2. And then you want to look at the coordinates of a point and decide whether it's an orange or a blue. In other words, does it belong in a concentric rings? Start with blue, orange, then blue, orange. I think I have the picture here. Yeah, so it's supposed to be circle, it's not scale, but basically you'll have, that's the picture that you want to learn. And to learn that, you generate points. The points are big dots, so I should have done smaller dots, but these are points. Let's say 10,000 points. And then you know the formula. So for each point, you can, since you know the formula, you can know which one is blue and which one is orange. Okay, so you create a data frame, x1, x2 color. And then you forget and just use the data frame and use that to learn to design a neural network that tries to predict this shape. And then you design, there is, so there is something called the heat map. Basically, the heat map is basically a 3-dimensional object, but used as a color, right? So your output assigns probabilities. So if you plot the probabilities, for example, 0 would be orange, 1 would be blue, and then in between you have a range of colors. And so when you draw the picture, then it will, then if it has done a good job, you will see basically an orange and blue. The orange means probability is 0 that it was a blue. It's probably 1 that it was, or very close to 1. When you see a blue, it means probably blue is 1. But then in between, usually around the boundaries, you may see, kind of different colors. That means that, well, it's maybe 40% blue or 60%. I believe it's 60. My belief that is blue is 60% or something. So you have a color, so you can visualize how it has it predicts the value. So that's one thing I want you to do. Yeah, it's a binary classification, right? basically we'll have only one value because you don't need to look at the probability that it's a blue, because the other one is just 1 minus that. Right? Okay. So now, it's out of my way. Okay, so let's now talk about, so I'm going to give you a quick overview of optimization process, and then maybe next week or the week after we go a little bit more detail into what kind of optimization algorithms are required. But here, basically, by the way, I forgot, I keep forgetting. Let me go back to these pictures. I want to show you something else. Remembering, then I forgot. So before I start, let me go here again. Okay, so, no, it wasn't here. It's this one. Okay, so what we call this network, right? For history, let me see. So I think it's wrong. Okay, I think it's network. No parentheses? Oh, I see. Okay, so here is basically the summary. When you use a network, that summary, it tells you the layers and what's going on and how many parameters it has. It's sometimes good to give to each layer a name, especially those layers that you are curious and you are in, especially when you have large. So here you haven't given any name. But look at the number of parameters. So the total number of parameters is about 670,000 W's. Now the data at about 60,000. So we have 60,000 data points, but almost 700,000 parameters. So if you were taking my course last semester, I would have told you, oh, this is horrible. You know, this is way overfitted. You have far more variables, more parameters than variables. Okay, but here, no problem. I mean, we have about almost 10 times, more than 10 times parameters than data points. About 60,000 data points, about 669,000 parameters, the W's. Okay? So that's when I was talking about overfitting. Doesn't seem to be such a horrible thing but don't overplay this, but it seems that overfitting is not that much of a disaster as it would be on classical learning techniques. This stuff about trainable and all that, we will come back to this later, but basically you are allowed to fix the W's or some of the W's. You said, don't forget about this, whatever these values they have already, that's it, don't touch them, but change these other ones. So we can actually set which W's. Now you may say, why I want to do such a thing? So there is a lot of reusing architecture. So for example, I trained my data on the digits. So there was a bunch of W's were computed. Let's say I say, okay, I want the first layer's W not to change, but only the second layers be fitted to this new set of pictures of clothing stuff. You can do that. Okay, and in fact, this reusing previously trained parameters is going to be important later on when we have gigantic models that will take forever to train. Okay, so that's what I was going to say, and I forgot. Okay, so now start talking about okay, so what do we have here? So we have basically, we have a loss function, which we have some model, some function that we believe connects the input to the output, some functional form. So it takes X, which is input, and outputs the Y, okay? And it has some functional form, and then there are a bunch of weights that it has to be determined, okay? So in this case, basically, as you can see, this is, as I said, W times X. You apply the nonlinear function, then you apply another W, maybe this is W1, W2, you apply a phi again, and so on. And then at the end, W and then another phi, and then that would be your Y. So that's the model, that's the mathematical formula for the model that is used in neural network. Composition of function. Achieving complexity by composing function over and over again. That's adding layers is all about. So I have some model, doesn't matter. What I'm saying right now is a little bit more general than even this. I have some formula, some weights that if I know what those weights are, the formula is completely determined. And we are trying to, and we have a loss function. And then we have a data. So the loss function basically somehow puts the first data point and the second data point, and then somehow, and you have the second, not even equal, I shouldn't say equal. And then that's a Y2, etc. I have n data points and Y. So I have these data points and the corresponding Y's. These are the observed Y's. This is what the predicted Y is. Let's call it Y hat. And the loss function basically is some kind of a penalty saying how different the Y hats are from the Y's. Okay? So if you look at this, you will have some formula here that involves a bunch of constants. Those are the data. The data are the Y1 through Yn and X1 through Xn. That's the data. The unknown is the W. And so this, we can think of this as a function of the W's given the data. And we are trying to minimize this loss function over all possible W's. Okay? So that's what the optimization is. So we talk about minimizing the loss, but in the maximum likelihood, you can think of it as the negative of log likelihood as the loss function. You're trying to minimize that. You're trying to maximize likelihood, but that means minimizing the negative of log likelihood. But that's the general formula. So what that means is that we need to have an algorithm for optimization, for minimization process. We need to have an optimizer. Okay, so one of the things in the context of machine learning, when they use the word algorithm, they really mean optimization. Of course, algorithm in computer science means a much general, much wider concept. But in the machine learning, when they talk about algorithm, 99% of the time they mean an optimization algorithm. So you can see that optimization is central. When it was going through, those when I was running the program, it was going 7 seconds, 5 seconds, 7 seconds. That was what it was doing. It was minimizing this. Okay, some loss function. So we need to have an understanding of what this process is. So let's, so here, I'm going to give an ideal situation, and then they say this is not actually what is happening in neural networks. It's happening in the simpler, like in the linear logistic function, or logistic regression, or linear regression, or things like that. So let's say our loss function, and I'm just assuming just to be able to draw pictures, I'm assuming I have only two parameters. I mean, 2 dimensions. So it's a 3-dimensional thing, W1, W2, and then the value of the loss function. But in reality, we know that we have almost 700,000 W's. But for now, let's pretend it's only 2. So let's say this is W1, this is W2, and let's say the graph of our loss function looks something like this. Okay. So we have a loss of W here. Okay, so that would be, if I had only 2 variables, the loss would be something like this. And then the idea here is to minimize this, is to find the point such that the loss of W at that point is as small as possible. So we are seeking this point. Let's call this W star, which is actually W1 star, W2 star, right? The point, the vector point. So we are seeking this point. Now, in 2 dimensions, of course, you can eyeball it, you can find it, that's not a problem. But imagine now that this is not 2 variables, like thousands upon thousands of variables. So now I'm going to make this into 2-dimensional by drawing contour maps. So if I look at the W1, W2 plane, and I can have something like this. Okay, so these are contours. Basically, what they are. So, for example, here you can see on the vertical line. If I put a flat, let's say this. Let's say this one. Think of it as if it's cutting through this. And this flat is, for example, size 2. And then maybe this one, maybe that's size, for example, 4. And then maybe I have another one over here. And then that guy has a flat. Okay. And maybe this is size, for example, 0.5. So basically, the contour map is the set of points on the W plane where the value of the function is fixed. So this could be 4, this could be, for example, 2, this could be 0.5, and so on. Okay? So basically, that's the projection of these guys. So in this plane, you will have this, you will have this, and you will have, you know, if I drop those things on there, that's what you're going to get. That's the continent. Okay, now how do you go about minimizing such a thing? So it's easier to geometrically visualize this. So I am seeking this point, which is the optimal point, but I don't know where that is, right? Especially when you're in much higher dimensional. So I randomly, well, at this point we have to initialize. I choose some point. I'm going to leave it open. How? For now, pretend it's some random point. Okay. So let's say I have a random point here. That's I will call this W0. This is my first guess as the optimal set of W's. So this, of course, also belongs to a contour by itself. So whatever my W0, W sub 0 is, f of that or loss of that W0, that's the contour. That's some number, presumably it's a large number. Okay, so I'm here. So then the question is, it's a bad point, or I don't even know if it's a bad point or not, but I want to make it better. I want to go to another point where the value of the loss is lower. Where would I want to go? What direction? There are in two-dimensional, there are like two-dimensional set of directions, but in higher, it's even worse. So one very simple idea is that you look at, if you look at this contour map, if you look at a tangent at this point, okay, then a vector that is orthogonal to this tangent, okay, if you go in that direction, it's actually, you get worse. But if you go to the negative of this, at least a little bit, not too far, if you go a little bit in the negative, the opposite direction of this normal vector to the tangent, you will go to a new point that is probably a little bit better, and you will call this W1. Okay? And you can actually go up to the three-dimensional thing. So essentially, imagine this is a valley, and you are in the side of the valley, and you want to go to the bottom of the valley. Okay? Now you have so many directions you can go in a horizontal thing, but of course, as you go horizontal, you also drop or go up on the side of this, the sides of this valley. So some parts are going to make you better. You go lower. Your goal is to go to the bottom, and some parts actually take you a higher place. So the one obvious technique, it's not actually practical, it's not how we do it as people, but maybe goats or some very skilled climbers can do, is that you could say, okay, the greedy approach is to go to the steepest place. So I'm here, I can go this direction, I can go this direction, I can go this direction. All of them take me, if I take one step in any one of these directions, I go to a lower point. But if I go to the steepest place, that one step gives me the lowest, drop. So that's a greedy approach. It does not necessarily imply that that is the fastest way to go to the bottom of the valley, but at least it's momentarily it's the fastest way from where you are. But once you have one step, the second step shouldn't be in that direction, because now the steepest might change a little bit this way or a little bit that way. So this direction, this is called the steepest descent. Okay, it's a greedy approach. And how do you define this direction? This direction is normal to the tangent, but the negative of that. That's precisely mathematically so I'm at W0. So I'm evaluating the function at W0 with all this other stuff. What is this direction? This direction is the derivative. So it is, since in this example, I have two W's, I have two derivatives, one with respect to W1 direction, one with respect to W2 direction. If I had 700,000 W's, then I would have had 700,000 derivatives, right? So for each variable, for each parameter, I have a derivative. So this function this is called the gradient with respect to the point W, with respect to the variable W, evaluated at where you are. Okay, so here, whatever these coordinates are, let's say, I don't know, 1 and 1.5, that's W0. I know the formula for the loss function, a bunch of logs and whatever, some complicated function. I need to take the derivative of this with respect to W1, with respect to W2. That gives me a two-dimensional vector, a two-arc vector. Negative of that will decrease the value of the function. So in other words, loss at current point minus the This is a two-dimensional vector. The gradient is just a vector of partial derivatives with respect to each variable. Two variables, so two variables of loss evaluated at W0. So I'm here and I go negative of the W. So this is, and then how far do I go? So I would put that alpha. Alpha is, I found the direction. How far should I go? A little bit, a lot, middle, whatever. So that's the alpha. That's called the step length in the lingo, in the classical lingo of optimizers. In machine learning, they call it learning rate. Okay, so that's called learning rate. Okay, so this is supposed to be less than, our objective is to make it loss smaller, less than loss at the original point. Okay. Okay. So where I am, evaluate loss at that point, evaluate the gradient. The gradient. So for example, if I have a function of, let's say I have an arbitrary function of, let's say W1, W2, W3. Okay, that's three variables. Then the gradient of G is a vector, a row vector. The derivative of G with respect to W1, the derivative of, I keep saying G, F is G, with respect to W2, and the derivative, partial derivative with respect to W3. So it's a vector. And in the W plane, that means it's a direction. The negative of that is called the steepest descent or the gradient descent. Okay, the GD, you may see the GD. So this is called the gradient descent method, or the steepest descent method. It's the stupidest, the simplest method you can think of. Okay? Now there is a whole body of research about gradient and optimization techniques. They are very sophisticated, but unfortunately they are not useful for machine learning. So my own field, when I got my PhD, was in optimization. And when I was doing my dissertation and the years following, we were doing my research, we were all worried about, oh, let's find so that it goes fastest and I get 7 digits of accuracy, 9 digits of accuracy, blah, blah, blah. In machine learning, we don't care about 7 digits of accuracy. We don't want that. It doesn't mimic, because the data is noisy. So 7 digits of accuracy you're fitting to the 7 digits of noise. So in fact, if you remember, the value of the objective function was growing very slowly. So yeah, so look at this. So loss function 22. So this gives me, it looks like I have here, so let's see. So up to here, I have 0.2 is kind of fixed. Then after here, it seems that 0.22 is kind of, well, not really. So really, if you look at this, it's not even giving me only barely 1 digit of accuracy, 0.2 or 19 or something like that. This is good enough. I don't need 7 digits of accuracy. Okay, so that's one thing. So that throws a lot of classical research in optimization not useful for this. It's useful for other things, but not for. And then the other thing is that, okay, for 2, 3, 10,000 variables, fine. But when you go to 700,000, and this is a baby problem we solved with 700,000. To keep in mind, the GPT-3, this thing that OpenAI has about 10 billion parameters. So the W space is 10 billion. Okay? So when you talk about 10 billion, even a vector of gradients is large. Now, there are techniques that you make a matrix, like the second derivatives, which is a n by n. Forget about it. No, you're not going to have a 10 billion by 10 billion matrix. So the classical methods of optimization are less relevant, and simple-minded methods like the gradient descent has become more relevant, because even though they seem very simple, but they are computationally better. Now, gradient descent is still expensive, and I tell you why, because if I have 10 billion W's, that means that at each point, I have to compute a vector, a gradient of as long as 10 billion. Now, computing the gradient for even one is not trivial. And we will see, you're not talking about functions like that you see in papers and like your textbooks in engineering and so on, which you could fit into like one little box. This is the function we're talking about. You know, this is a gigantic function. It's a very complex function. You're trying to take derivatives with respect to W with the composition and multiply and composition, and then more complex forms like this is even more difficult. So the process of taking derivative is non-trivial. And then we also have hundreds of thousands at the least to billions at most number of derivatives. But the point here is that this is why you need the derivative, okay? Because so the algorithm is now very simple. The gradient descent sketch algorithm is very simple. So you're trying to minimize the function. I'm just going to give it general, not in the context. So just you have minimum W1, etc., WD. Okay. So you have a function of V variables, and you got to minimize that. Step one, guess an initial point. There are some nuances on the initial point. I will discuss some of them in future lectures. So let's call this W0. This is the vector of W's, right? 2, then you say for or repeat. So you will say repeat this process at the kth iteration, compute G of W1K. So I'm in the kth iteration. I find this is the kth, my kth guess. Okay, you compute this. Let's call this the direction D. And then set WK plus 1, the vector, to be the old W minus some alpha times the direction. Take the derivative, go to the negative a little bit, about alpha, then that's a new point. Take the derivative again with respect to this new point, go in the direction. So that's basically the idea. So if you want to visualize this, so basically, what I do, I'm here, I'm going to go here, then at this point, I'm going to go here, and then at this point, I'm going to go here, and then at this point, I'm going to go here. Now, this is too nice. I got that, but you could have situations where you go zigzag a lot before you get to the optimal point. So you may each zig and a zag is one iteration. So here I didn't say where to stop. The process conceptually is infinite. We never get to the point, but we get closer and closer. But you have a criteria. For example, The goal here is to make the optimum, by the way, is when the gradient is equal to 0. Just like the one-dimensional case, when you take the minimum, the derivative set to 0. In the multi-dimensional, all the derivatives are 0. In other words, the gradient is 0. So one criteria would be, of course, the gradient never goes to 0, but gets smaller and smaller and smaller. So you can say a tolerance like 10 to the minus 3. If the norm of the gradient, if the length of the gradient is 10 to the minus 3, for example, or less, then stop. You're close enough. Okay, so that could be a criteria. There are other criteria like the difference between WK and WK plus 1 is nothing. In other words, it hasn't moved at all. It's just stagnating. So that means you're already close, or you cannot move any further. So that's called the gradient method, basically. That's intuitively. Now, there's some theory which I'm not going to discuss. First of all, why does this converge? I mean, intuition is good, but in mathematics, you have to prove because there are all these real counterexamples and so on. So why does this converge? And furthermore, how fast does this converge? What's the rate of convergence? The rate of convergence, basically, it means that, for example, when they say it's a linear rate of convergence, it means that after a constant number of iterations, you get another digit of accuracy. So for each digit of accuracy, you have to run approximately a constant or one constant number of operations. That's called linear convergence. This is actually pretty good linear convergence for machine learning. But in a lot of other techniques, more practical, the convergence is much slower. Okay, so we have to worry about that. But Professor Mert Gurbuz-Balaban teaches a course called Optimization Methods for Machine Learning. And that's what that course is all about. All the various algorithms that are suitable and applied for different kinds of machine learning problems. One of them is, for example, for neural net. Okay, so we're a little bit over the break time. So this is, so far, it's very rosy. This is for a simple loss function. Neural network is not at all like this. The type of functions we are going to minimize is much, much more complicated. So we're going to discuss that. So 2:43, let's take a 5-minute break, come back around 2:48, and we will resume.
Professor, I think you're on mute.
Yeah, sorry about that. Okay, so in the classical machine learning, regular logistic regression, linear regression, and so on, something good happens is that most of the loss functions, common loss, not everything, not all of them, but most of them have this problem that is properly called convexity. Convexity, if you want to look at intuitively, it means bowled up like a bowl. And in particular, it has a unique minimum. There's only one minimum, okay? If you want to have a technical definition of what convexity is, I'm going to give it for a one variable function, but it's exactly the same for all variables. So basically, if I have any 2 points, and so this is f of x, so I choose any 2 arbitrary points. This is f of x1, this, the height of this, the height of this is f of x2, the height of this is f of x1, okay? And take an arbitrary point in between them, okay? Now, if you draw a straight line between f of x1, so this point is x1 f of x1, this point is x2 f of x2, right? If you draw a straight line and then choose an arbitrary point in between x1 and x2, then let's call this, I don't know, let's call this like x3, okay? So f of x3 is always less than basically where x3 will hit that line that combines these two. Okay, it's a bold chop. Now, if it's not a convex function, like if it is like this, then obviously that's not always true. So for example, between these two, and then I can have this, and here, in this case, it falls below, not above f of x3, okay? So this function, this is a convex function, this is a non-convex function. Okay. Now, why do we care about convex and non-convex? So, in general, a convex function means that basically, if you have any 2 points in the domain of the function, compute their f's, connect those 2 f's with a line, and then take a line that connects those 2 points, and point any point above it, the value where it hits the surface, the graph of the function, is below that line. Okay, so that's a convex function. This is a fancy way of saying that basically this function is bold up. Okay, and the key property is that there is only one minimum. Such a function has one minimum. Okay, so that's good. If you're trying to minimize this function, you're only looking for one thing. The one minimum is what we call global minimum. If the function is not convex, like the second one over here, there could be lots of minimums. For example, in this case, it has 2 minimums. Okay, so I'm here. It's a local minimum because I am smaller than all the points nearby. If I go anywhere, I'm lower than those guys. But if I'm here, I think I'm the minimum, but if I have to go up and then come back down, and somewhere else is even lower minimum. Okay? So kind of like, it's an example of for example, if you maybe hiking in New Jersey, maybe in the Watchung Mountains or the New Jersey Water Gap or something, and you want to go bottom of a valley, and then you go to bottom and you think that you are in the lowest point on Earth. Well, you're not. You're just the lowest point on that small neighborhood. Maybe somewhere deep in Peru or in China or some, or if you even count the oceans, even worse, near Chile or someplace, that's far lower place. But then think about it. How would you know? I mean, if you are a Martian coming to New Jersey and then go to, Delaware Water Gap and go to the lowest place, how would you know that this is not the lowest place on Earth? Not knowing anything about the surface of the Earth, other than, it could go ups and downs. You could be, as far as you are concerned, you could be in the lowest part, but it could be, there are much, but even and how would you find the lower point or the lowest point that is, very far from you, or it could be very close from you? Other than, think about it, other than essentially covering the entire surface of the Earth to find out the lowest point, there doesn't seem to be any other logical way to find it, right? So when we have a non-convex problem, the gradient descent works, but it finds a local minimum. It only is guaranteed to find the local minimum, depending on which initial point you chose and how the dynamics came out, and you randomly may converge to one of the local minimum. Okay? Actually, I'm lying a little bit because it could be even worse. Because what gradient descent is finding is a place where the gradient is equal to 0. When you have a function that is convex, then where gradient is equal to 0 is essentially the same as minimum. The gradient here would be flat. That is, that's essentially the same as saying it's equal to 0. The slope is equal to 0. But there are, if you have a non-convex function, there are places where the slope is 0, but you're not minimum or maximum or anything. For example, again from calculus 1, if you're here, you see the gradient here is 0, but that's called an inflection point. If you're going this way, you think you are getting to the top of the world, but if you're coming this way, you think you're going to the bottom. Okay, so that's called an inflection point. So the gradient descent can converge to such points, because what it does is trying to minimize the basically the gradient, but at least what if the stopping criteria is the gradient. Okay, so let me show you a little bit more interesting picture if I can find. So I don't know. So yeah, okay, over here. So for in two variable, this is the picture of a landscape that has lots of minimum, lots of maximums, and then you have places like this that are called saddle points. They're like a horse's saddle. This way it looks like a minimum, but this way it looks like a maximum. Okay, and then so this type of function, minimizing this, finding the minimum of the minimums, is called the global minimum. That is very difficult. It's the number of minimums would be exponentially large as a function of the number of variables. So here I have only two variables, x1 and x2. But when you're doing 700,000 variables, like that, the model we made, then there is then our bets are off. So there could be lots and lots of minimum or lots and lots of saddle points. So essentially we are now. Why am I saying all this? In classical machine learning, regular linear regression, linear polynomial, blah blah blah, logistic regression, linear regression, even support vector machines and things like that. The minimization, the optimization process we are dealing with could be difficult in situations. Like linear regression, there is actually a formula. We don't even need to use gradient descent. We know mathematically, analytically what the minimum is. In that case, we are lucky. In the logistic regression, there is no formula, but the gradient descent or something like that works. There's only one minimum. It's a convex function, so we are still fine. By the way, the maximum likelihood is not the maximum likelihood is not convex. The log of the maximum is convex. So that's or negative log is convex. Okay, so when you put the log, it becomes convex. Ordinarily, it's not. But anyway, so there we are lucky. Now, why are we unlucky? Well, the situation with the neural network is that we are not that lucky in this case. Now, why is that? Let's look at the simple linear regression. So in the linear regression, remember, basically the loss function was, so this is basically the case where you have a bunch of x's, the vector of x and a y. And then you're postulating that y is a w transpose x, and the w is what you want to know. So in this case, the loss function as a function of w, given the data, that is given the x's and the y's, is sum of squares. So it is basically the real yi minus the predicted yi, which is w transpose x squared. So you sum 1 through n. This, as a function of w, is a convex function. In fact, if you take its derivative, as this is in the notes and I mentioned last time, if you take its derivative is linear. So setting the gradient, what we are trying to do, we are trying to solve this equation, this system of equations. The gradient has as many functions in it as there are w's. So if, like, for example, there are 10 w's, that means the gradient is the derivative with respect to the derivative of loss with respect to w1, etc., etc., the derivative of loss with respect to w, for example, 10. So that would be the gradient of loss. Okay? So the minimization problem is trying to set this equal to 0. In other words, we're trying to solve this system of equations. The system of n equations in n unknowns. Unknowns are the parameters. We have as many derivatives as there are parameters. There's a system of equations. Now, in this case, linear regression, we are very lucky. So this is actually a nonlinear system of equations, a mess, but in general. Now, in the case of linear regression, that special case, we are lucky. Because look, this is a quadratic function of squares. When you take its derivative, you get a linear function. So the derivatives are all linear functions. So we have a linear system of linear equations. That's matrix algebra. That's the libraries, easy peasy. You solve that. It's not quite easy peasy computationally, but at least we know how to handle that. So that you have a formula. And in fact, in the notes that I probably gave you, I have actually explicitly said what the formula is. When you get to logistic regression, it's more complicated. It's not, you don't have a formula. You have to use an iterative process like the gradient descent. But it is a convex function, not the loss function, but the log of the likelihood function. When you put the log, it becomes a convex function minus the convex function. Iterative method like the gradient descent solves it. But now, when we go to neural network, we use exactly the same formula. So our loss in neural network, W given data, is essentially the same for the regression. Now, I'm not talking about classification. I'm talking about the simpler case, the regression. 1 through n, just like that, yi minus, but now this is not our model. Our model is this monstrosity, this w1 x times, apply phi to it, multiply by w2, apply phi to it, etc., etc. And then after a bunch of times, and then that's our model, right? That's by definition the type of function the neural network is trying to compute or pop. So then this squared, this as a function of W is a huge mess. And it is not convex. By the way, we don't have one W, we have lots of W's, and each one is not a vector, it's actually a matrix, but doesn't matter. Put all of them together and think of the whole thing as one big W. Okay? As a function of that, this is not a convex function. This is more like this function. This is more like it goes up and down, up and down. Okay? Not in two-dimensional space, in the 700,000 dimensional space, at least for that baby problem that we solved. So imagine the difference between a linear regression where the model is W1x1 plus W2x2, etc., versus a regression with a neural network, which is phi of wx times w times phi times, and this messy composition. So, and then the number of w. So now we have a thousands, tens of thousands of w's. So this gigantic model, and it's not even nice. It's not even convex. It's up and down, up and down, up and down. So many minima. So when we apply gradient or any other algorithm to find the minimum, which minimum does it find? And which minimum is the correct one? We don't know. It could, in fact, there could be many. In fact, you can run the algorithm once with one initial point. You get one W. You may run it again, the same problem. You can give it to your friend. He uses exactly the same code, except that the initial point he chooses is something else. It comes up with a completely different W. Okay? And here is another mystery of neural networks that nobody understands. An arbitrary function, the minima could be different. Some minimum could be over here, then you come over here, then you come over here, then it could be all up and down. The minimums are not the same. Some minimums are very large, some minimums are very small for an arbitrary function. It turns out that for neural networks, the minimum, and this is again not understood mathematically, the minimums are roughly equal. Not equal always, and you can find exceptions. But for most problems, the minimums are roughly the same. By the way, so this is a mystery that people is not quite understood what's going on. So that means that you can start your initial point wherever you want, although there are some heuristics for that. And then wherever you end up converging to, whatever local minimum you're converging to, that's good enough. Okay? So that's so that was kind of like a good news, bad news. The bad news that is not convex, so there are tons and tons of minimums. The good news is that most of the time, they are more or less the same. The value of the loss function is the same. So it's kind of like this, basically, if you want to visualize it for one-dimensional situation. It's kind of like this, as opposed to like this. If it was like that, it would be disaster because the minimums are up and down. Which one do we converge? Which one are we lucky to converge to? If we converge to this one, it would have been horrible. If we converge to this one, it is better. But the neural network loss functions more or less look like this. All the minimums are the same level. Not exactly the same level, but roughly the same level. So this is one of those mysteries that is not quite well understood. It's not always true, but it's true most of the time. So it's something that people, PhD students and so on, and researchers are pondering on. Okay. So, any question? So this is the reason why we need to worry about the derivative. So we are not talking about, in the optimization process, we're not talking about the function of the weights. The number of weights could be tens of thousands to hundreds of thousands to millions, depending on how complex of a model you're choosing. And we need the algorithm on the table. There are many different algorithms, by the way, and we are going to see some of them. But the algorithm, the table is the gradient descent. So we need, given this loss function, for regression we use this and for classification we use log of that other formula. But it's essentially you have the formula like this. You're trying to find the W, so the data come in here, and then you sum over all possible data points. So but the data is given. They are fixed numbers. You can't change the data, but you are supposed to find the W's. So we need to compute this function. We need to be able to compute loss at a given W, and also compute its gradient at a given W. That is computationally expensive, right? Because if you go back, what is going on here? Here's the W is a matrix, you multiply it by X, so it's a matrix vector multiplication, followed by applying a phi, the activation function. Then you get another vector, then apply another matrix vector multiplication, then apply another phi, and so on and so forth until the end. Okay, so when the models are large, W's are large, there is a lot of multiple just to evaluate the function at a point is expensive. I mean, it's not expensive in the sense of algorithms and NP completeness and so on, but it is expensive because you have lots and lots of data. But even worse, you have to compute the gradient. And if I have 700,000 W's, that means I have to compute 700,000 gradients, each of which is a messy function. It's kind of like a squaring the amount of work. This seems that at the outset is a complicated process. And on top of that, how do you write the gradient? You can have a database of simple functions, log, e to the x, logistics, softmax, blah, blah, blah. For each one of them, you can write a code for the derivative function, the corresponding derivative. That's not hard. But now we are talking about composition of functions and composing this with that, fairly messy. So we need to have a systematic approach to evaluating the function and evaluating its derivative, or actually the gradient, derivative with respect to all variables. So how do we go about doing that? So there are in the classical so there is a field in computer science called numerical analysis. That's basically what we're number crunching. And numerical analysts have methods for computing a function and its derivative and so on. Derivative is actually from a numerical point of view, is a little bit nasty. But anyway, there are techniques like that. But we are not talking about a really simple function. It's one of the things that machine learning and in particular neural networks has come is that they have brought down the old problems that were assumed to have been solved, and then they realized the known algorithms are kind of useless when those algorithms were good when you had 1,000, 10,000 variables and items, but when you go into hundreds of thousands, billions and so on, then they become impractical because you can't even fit the thing into the memory, let alone into the memory of a regular function. So here is how you approach. So first of all, observe that you're dealing with composition of functions. Okay, so composition of function is I have a function called f of x, another function called g of x. The composition is f of g of x. Right? So that's what is called the composition of two functions. And this is exactly what neural networks do, right? They W phi, apply W, apply phi, apply W, apply, so it's a composition. So suppose in just single variable case, again, you have to remember a little bit of your calculus here. Simple variable case, suppose I know the formula for the derivative of this guy, and I know the formula for the derivative of this guy. Okay? What is the formula then for the derivative of this guy? So it's called the chain rule, right? You have you have the derivative with respect to g times the derivative of g with respect to x. So to give you an example, suppose I want to compute the cosine of log of x, the derivative of that. Now I know that the cosine is what? Minus sine, right? And I know that the derivative of log is 1 over x. Okay? So to apply the chain rule, what do? I pretend that this is a variable. So I call this, y. So it is essentially so the derivative of respect to y, that is minus sine of y times 1 over y, which is 1 over x. And so, which is equal to minus sine of, what is y? Y was log of x divided by x. So that would be the technique. That's the chain rule. So since in neural network, we have phi times w times another, apply phi again times some sort of a chain rule, but except multivariable version of it is in play here. Okay, so this is something to keep in mind. So the first thing is the chain rule. The second thing is so there are several approaches, but some of you may have worked with Maple or Mathematica or some things like that. That's called symbolic calculation. So one possibility is to use something that Mathematica is using and use a symbolic formula. What the symbolic does is that you give it a function and it writes the code for the derivative. That's doable. That's done, but it is excessively expensive when we are talking about hundreds of thousands and billions. So that's out of the door. Another thing is to just go at a derivative at a point to just do a pointwise thing. So for example, if I have a function f of x, remember that the definition of derivative is f of x plus epsilon minus f of x over epsilon. The limit as epsilon goes to 0. So instead of 0, you can say, oh, I'm going to use 0.001 or 0.0001 and do that. Okay, so that sounds simple, but it has numerical issues. When you're mixing up large and small numbers, you're always going to get into trouble. Okay, so this is, while we can use this, it is a terrible approach to computing derivatives. So what does this do? Well, how do we actually do this? We first we have to talk about computation graph. So this is where I'm starting to talk about backpropagation algorithm. So first, your formula, your function, is actually composed of, can be broken down into simpler function. Simpler, 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 until you basically break it down to add, multiply, divide, subtract, e to the x, log x, these simple functions, right? So you can get a more complicated function by creating a computation graph where each node is a simple function, or at the beginning, the variables themselves. So the variable themselves is a simple function of itself, is identity function, right? F of x is equal to x is a simple function. And then by graph composing it, so let me show you an example, because that's a simpler thing. So let me make it messy things like cosine of log of x plus y times x squared plus 1 times the sine of exp of 2x plus y cubed, okay? So it's just totally random, nonsensical function, okay? So you can, so what is the computation graph? So first of all, what are there are variables and there are some constants. So there is x, there is y, there is 1, and so on. So I start from the x, and the y, and then maybe there's a 1 here, so there's a 2 that is multiplied, okay? And then you start, yeah. This e to the x, or exp. Yeah. Okay, so then you can start like, okay, I need an x squared, so I go to square. So this is a unary function. X squared is a unary function. So x, so that comes x squared. Then there is a multiplication. That's a binary. So I multiply these. So that gives me this. Okay. Then I add this, and then I add again to get, oh, sorry. Yeah, so this, I may run out of space, so yeah, okay. So this whole thing is just this part, right? So then I apply, Then I apply log. Log is always natural log unless it is stated otherwise. So that takes care of that. Then I add a plus. So then that's that. Then I add a cosine. Then that's this whole thing. And then I now need 2 and x again, multiply to get 2x. Then I add y. Oh, I have, well, y cubed is y times y times y. So I have to basically, yeah. So yeah, so you can have it ternary operation. So cubed. That's y cubed. And then you add this 2x together, and then you apply exp, and then you multiply these two. Oh, I forgot a sign. Oops. So yeah, then I have a sign, and then I multiply. And then this is f. Okay, so there is a graph. Now, I assume most of you are computer science have seen what graphs are. So graphs are basically nodes and links. So we can model any mathematical expression composed of atomic objects like inputs, variables, and then maybe simple function. And what is a simple function? Whatever we define. We have a repertoire of simple functions, basically, and then you can use those. And then any other complicated function can be made into a graph like this. Okay, but what's the point? So what do we want to do with this? So in this case, this is 2 variables, but I can have several variables, many more variables. So the first, so let's call this thing f of xy. I want to do 2 things with this. Given some value, some arbitrary value. So let's say x is equal to 0.2, y is equal to minus 0.3, some random values. I want to compute, so this is, let's call this x1, y1. I want to compute this. I want to be able to plug in the values of x and y for a specific values, and then compute this. So I'm going to be a little bit rough here, but the idea is basically you traverse. So, but this one thing I forgot to mention is that we should actually assume this to be. We are taking this to be a directed graph. In other words, I have to put arrows here. Now I didn't put arrows, but assume that it's going. The direction is from bottom to up, right? So it's really a directed graph. It's not an undirected graph, so you can't go backwards. So one of the things you can keep in mind is that such a graph is acyclic. Acyclic graph means that when you start from a node, if you have a cycle, that means you can start from a node, walk 2 points, and then somehow come back to where you started. Then such a thing is called a cycle. An acyclic graph is a graph that does not have any cycle. Once you leave a point, a node, you can never come back to it. Okay? Now, convince yourself that any mathematical expression, when you put its graph, the corresponding graph has to be acyclic. Because if it is cycle, that means a node is defined in terms of itself, right? Now, that is actually not a weird thing. We have such a thing as recursive functions, which we come back. There are neural networks that are recursive, that they're all cycles. We would put that aside for now, okay? But in general, an ordinary, normal-looking expression that it is not defined in terms of itself should be an acyclic graph. So it means that I come from the beginning. The beginning are some nodes that are the in degree, things that come into it are 0. These are the initial things. This guy, this guy, this guy, this guy. There's nothing, they're just given. The values are given. There is nothing, they don't have to wait for somebody else to find out what their values are. Those are the initial point. And then all other nodes can be computed once all the inputs that come into them, their values are known. So for example, here, this square guy, this guy, needs to wait for x to be known. Once x is known, then it can find x, then it can apply the square operation to it, and then it will be output. This product here has to wait, since it has 2 inputs, it has to wait for y. It also has to wait for x and the x squared to be calculated until x x squared times y is calculated. Okay. So now you can smell something here. There are parts of these graphs that are sequential. That is, a node cannot be computed unless its predecessors have been computed, right? Unless what comes to it, the nodes that send arrows to it are already evaluated. So essentially, if you take a longest path, a long path, that is kind of like the bottleneck. If the longest path from an input to an output to the F, let's say has 10 steps, and let's say each step requires 1 microsecond, then that means that you have to wait 10 microseconds to get to that, at least 10 microseconds, maybe more. But if there is a path of length 10, you need at least 10 steps to get to that point. So that's kind of like the bad news. There is a sequential aspect to it. But there is also a good news. There are nodes that they have nothing to do with each other, and therefore they can be computed in parallel. If you have idle CPUs or whatever sitting around. So for example, while I'm doing this square, this cube guy here does not need that, does not need that, does not need that. While I'm doing the squaring and multiplying and doing this part, I can have another computer in the next place doing the cubing and then the adding and so on. Those things have nothing to do with each other. So this gives you the concept of parallel computing. So a given computation graph like this, which is acyclic, doesn't have any cycles in it, there is an algorithm that can be broken down into pieces. Now, one approach is to assume I have an unlimited number of GPUs or processors, and so I can use as much as I want. Another approach is that, no, wait a second, I don't have an unlimited number of GPUs. I have like 10 only or 20. And so I have to break this down into blocks of 10 parallel things. So this operation by itself is fairly, requires some algorithm. Okay, I'm not going to get into the details of that. But the basic idea is that to evaluate a function like this, I start from the bottom, node by node, level by level. I calculate each node. Once the node is calculated, it's ready to feed its value to the next guy. The next guy has to wait for this guy and also any other guy that is feeding stuff to it. And once everything is available, it calculates and feeds it away and so on. So you basically can do if you're doing a sequential, you can do a breadth first search or something like that. But there is a parallel search if you have idle computers available to you. So essentially, let's agree. I'm not going to give the algorithm completely, but essentially, listen that we can compute this graph proportional to the longest path from a input to the output. The longest path. By the way, I showed only one output, but there doesn't have to be just one output. There could be multiple functions. Like, for example, in the logistic regression, we don't have one F. We have, if there are 10 classes, we have 10 probabilities. So it's 10 functions. So there doesn't have to be just one F. There could be multiple F using the same variables and the same inputs. Okay, so you have a bunch of input nodes. Those are the initial variables or a bunch of constants. You have a bunch of output. Those are the final Fs that you are trying to calculate. And in between all the messy operations and so on, some parts are shared, some parts are not shared, and so on. And there has to be a clever algorithm that basically the clever algorithm is if you have just one computer at hand, is you can do breadth first search from starting from bottom and going up. If you have multiple, then you have to break down, decompose the graph into parallel disjoint paths, and then run those paths simultaneously. Okay, so that's something. So this is called for evaluating the function at a particular point, we go this direction, and it's called forward. This is called the forward pass. So the forward pass is to sweep through the graph from the bottom to the top. So when I'm optimizing, or not even optimizing, when I'm trying to suppose I have the W's have been calculated in the neural network. Now I want to predict. So that the neural network actually itself is the computation graph, right? You have X's, a bunch of W's, multiplied, you get the Z's, then you apply the feed, then you have that. It is actually the neural network, if you draw it, is actually the computation graph, except that it's going from, left to right as opposed to bottom to top. Right? If you think about it, that if you draw the graph, that's basically what it is. Okay, so we have the forward pass. But now, what about the derivative? Now, on top of that, I want to compute the derivative of f with respect to x and the derivative of f with respect to y. And y turn into. So, but at a given point, I'm not interested in the formula. I'm interested in computing this derivative at x equal to 0.2 and y is equal to minus 0.3. So at a given point, I want to compute the gradient, the two, in this case, only two variables. How do you do that? So what do we have at our disposal? We know that for each node, there is some well-known function. We know its derivative, like that exp. We know that its derivative is exp. For that log, we know that its derivative is 1 over x, 1 over whatever the input is. But it's also composition. So we know that stuff. We have code for each one of these well-known functions. Okay. We also know that because this graph is essentially visualizing composition, you know, this applied this function, then apply that function, and apply that all the way to the end. So it's made of a bunch of compositions. And we know that for composition, we need the chain rule. So our tool is the chain rule. So here, we start from the top and go backward. Okay? So for example, I am interested in the derivative of x with respect to x, the derivative of f with respect to x. That's too far. It's a mess. So I start from the top. I know that, for example, the derivative of f with respect to f is equal to 1, right, at the top. So now let's give these intermediate guys names. Like, for example, let's call these n1, n2, n3, n4, and so on. Each node has a name. So, so now I want to calculate, for example, well, this should have actually be, let me call this n0. Well, I'm sorry, that's just f, forget it. Okay, so now here, for example, this is, let's look at this. Let's look at this node. What is the derivative of f with respect to n1? So n1 is cosine of something. I don't care, I call it n1. F is just n1 times n2. Right? The derivative of this is just n2. Right? F is n1 times n2. I don't care if that n1 and n2 themselves are something else. At least in terms of n1 and n2, the derivative and the derivative of f with respect to n2 is n1, because this is just multiplication. Okay. Now let's look at, for example, n5 here. So the derivative of, so here is, so think of this graph, but orient the arrows. When you reorient, go back up, the arrows are the opposite. So now the input is the f, the top, or whatever number of functions I have, and the output at the end will end up with the derivative of x with respect to each one of those f. So I'm going backward. So now I want to do the derivative of n5. Where is it? N5 is here. So the derivative of n5, the f with respect to n5. But by change rule, now this guy has things coming out of it. All of those guys' derivatives have to have been already calculated before I can come to this node. So this node, the only thing that is coming out of it is this node, which I already have calculated its derivative. I can only calculate the derivative of this guy, this EXP node, only if everything that comes out of it, the nodes that are coming are reached from there, is already calculated. So in this case, there is. So now this is where you use the chain rule. Derivative of f with respect to n5 is equal to the derivative of f with respect to n2, which I already have calculated, times the derivative of n2 with respect to n5. Right? So that one I have already calculated. That's n. That's what do you call it? That's 1. I don't know why I call it n. N1, right? Sorry. So this is n1 times, and then the derivative of this with respect to n2 is sine. Sine of something is cosine. So times cosine of n5. By the way, since I have already computed the values of n1 and 2 in the forward, I'm all ready to plug in the numbers. See, this is n1, the functional value. But I already have calculated that in the forward when I was calculating the function. So these numbers are already calculated. I have already saved those. So when I'm going backward, Now that I need to multiply n5 or n3 or whatever to multiply that, I know its value, so I can actually numerically calculate that. And you go this way, all the way down. So when you have a situation like this, where you have several things coming out, you have to take the derivative with respect to each node and then sum them, add them up. So you need to have derivative of this with respect to this point, derivative of this with respect to that point, and so on, and then you add them up. Okay. So this is called the backward calculation, and it's called that. This whole algorithm is called the backpropagation algorithm. That this whole process is what, when you hear the word backpropagation, that's it. And it is a general approach. It's really not restricted to neural networks. Any mathematical expression made up of a bunch of variables and a bunch of known functions whose derivatives you have already have access to, individual derivative of that function, can be composed in any which complicated way, can be visualized or modeled by a graph like this, and then at given points for x and y and so on, you can calculate by forward, by going from bottom to up. You can value each node until you get to the final functions. The value of those functions at given points can be calculated. That's the forward. And then if you're also interested in the derivatives, then you go backward calculation. Okay. So that's basically that. And if you, I have been giving this a loose way, but here is basically what you want. If you want to know what the complexity of this algorithm is, basically you have to do one calculation, well, two calculations per edge. Per edge. Each edge that you walk involves some, I'm assuming cosine, sine, etc. These are all equal amount of time. Okay, assuming that cosine, sine, all these atomic functions, multiply, divide, etc., the equal amount of time, then each calculation, each walk through an edge involves a calculation. Now, if you have a binary operation like adding, so it needs two, so you can count that as two operations, two operations. The point here is that forward calculation involves, so if you have one function, forward calculation involves proportional to the number of edges, essentially. Now, backward calculation, you have to do, if you have several f's, that means you have several gradients. Okay, so for each gradient, you have to sweep through the graph and traverse the graph. So if you have so in this case, the bad situation would be when I have like thousands of functions, outputs. Then that's not that, because for each one you have to go through the graph. Okay, so that's scaled linearly with the number of functions. But the interesting is that the number of inputs can be as large as you want. I mean, it's that if the whole thing is proportional to the size of the graph, it's not going to be more than the size of the graph. I can have thousands of input variables, but the whole operation is proportional to the size of the graph. It doesn't matter. But if I have thousands of outputs, for the backward operation, I have to go through for each one separately. Okay, so that's more expensive. Now, in practice, most functions that we calculate, the number of functions are small. I mean, think about it. The simple regression has just one output. Logistic regression, if you have k classes, classification problem with k classes, you will have k probabilities that you have to calculate. So that means k outputs. Most of the time, the number of classes is small, like in the digit sort of fashion and so on is 10. There are cases like ImageNet. One of the things we're going to see, the ImageNet is basically a gigantic set of pictures that Google generated from people, when they posted something. And there are 1,000 categories. So there are 1,000 objects like trucks and cars and monkeys and frogs and ball and anything. 1,000. So there, if you're working with images with 1,000 classes, then you have 1,000 probabilities. If you're doing classification, 1,000, you have 1,000 Fs that you have to calculate. So that's basically the backpropagation. Now, what time is it? I have only about like 3 or 4 minutes. The beautiful thing about this is that not in the Keras, but in TensorFlow, you can do this all automatically. So one of the things that TensorFlow does, you don't draw the graph, but you write down one line at a time each node's expression. So you will say, okay, I have an X. So first of all, you have to declare what are your variables. So in this case, I will say X and Y are my variables. Okay. And then I will call this, for example, N12, or this is square. And then so N12 is X squared, N13 is whatever. For each one of the nodes, I will write the corresponding formula and give it a name. And then you can simply call the gradient, and it will run through this process and will calculate the gradient for you. And the process that it does is exactly that. So since time is not, we don't have too much time, I'm just going to do it quickly. I have posted it, and then next time I will go a little bit more in detail. So is that the one? Yes. So here I have simple derivatives with tensor. So by the way, I'm sure if you have downloaded everything recently, you have TensorFlow version 2. TensorFlow version 1 is different. So when they upgrade, they don't make it backward compatible. So whatever you wrote for that, if you guys probably don't care, but this is my 3rd or 4th year that I'm teaching. So I wrote a bunch of stuff for TensorFlow 1, and then long and behold, next year it was TensorFlow 2. I had to throw everything out and rewrite the whole code again. So anyway, so here, let me show you. So here is the function. I don't know what that star is. Some simple function, right? F of x1 and x2, cosine x1, e to the sine of x1 plus cosine, something simple, okay? So, so first of all, you have to declare x1 and x2 as variables, okay? So here you say, so I've imported, where is it? TensorFlow as TF, okay? So x1, x2 are TF dot variable. You can initialize, for example, I am interested in computing this function at pi over 3 for x1 and pi over 4 for x2, just some arbitrary value, who cares? So you would do that. Now, one thing, I don't know if there is a tf.pi. So as I told you, TensorFlow and NumPy are all very similar. So I think I'm fine using NumPy. I don't know if there is a tf.pi. If it is, better to use tf.pi. But if not, that's fine. Now, one thing, very annoying, but it is necessary. When I divide by 3, if you say just 3, it will give you an error. And that's very annoying because there is all languages, all systems have automatic type conversion. So if this is an integer and this is a real float, it's supposed to turn the integer into float and then do it. TensorFlow doesn't do that. And the reason is because, again, think big. Think millions of variables are gigantic because that's what's designed for. The process of type conversion is expensive. by a constant factor, but we are talking about hundreds of thousands of these things. So they say, the hell with it, we are not going to do it. You, the user, is responsible. Your responsibility to make sure that when you're adding, subtracting, dividing, doing things, that these are same type. And there isn't just one float. There is a float 32. There's a float 64. Make sure all of these are the same. Now, there is a cast function, tf.cast, but then the point is you have to do it explicitly. Okay? So if you have to take a floating point and turn it into an integer, you have to do it yourself. So make sure that you put 3.0 or something like that in there, or 3 point is enough. Okay, now, I'm not going to get into this gradient tape, but the idea of gradient tape is that, remember, forward, it calculates the nodes. It has to remember what those values are. That's what the so-called tape is. It puts it somewhere. It's like it's scratch pad. As it goes forward, it calculates the values of each node so that when it goes backward, you can reference them and take it. So that's what the gradient tape is. The syntax, we don't have time. We get it like this with statement. You have to remember what it is. So here I have F1 is cosine. Remember, it's TF.cosine, not NP.cosine. All of things have to be TF. T2 is sine, etc. F3 is x plus 1, blah, 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 blah. And then at the end, F is, that. So it's basically algebraic form of this function here, okay? Now from here, you can draw the graph if I ask you to do it. It's not hard, but here, that's what it is. And then G is T dot gradient. Yeah, the gradient is the function, it knows. You give the function F, that's a node, and you have to give also the list of variables. That's x1 and x2. And it will find it for you, and then you can print it. Okay, so I can run this just to show you. Okay, so here, this and the gradient, as I said, is minus 1.36, minus 1. So if I was doing gradient descent at this point, and my initial point were these guys, right, 2 and 3, then now I have the gradient at this point. It is minus 136 and minus 177. So the negative of the gradient, that's the direction I will go to improve. Right? So that's the gradient. And so this is a good time to stop. So study this. I have put 3 of these. So there is this one. There is one that does Jacobian. Jacobian is when you have multiple outputs, multiple inputs. So a gradient is when you have just one function. So you have one vector. If you have several functions, you will have several vectors on top of each other. So that gives you a matrix of variable derivatives. It's called the Jacobian. They just use fancy names for simple stuff. So there is one in Jacobian. I will discuss this next time. And then I even have one for a function that is defined kind of recursively, but in a way that it is not a cycle. So we'll discuss that. So yeah. So if there's no question, I'll see you next week and study these. And I have given you the chapters on the book. The book is very good, well written, so you can read this. And the back propagation is defined in Appendix D. There is another algorithm. I will go over that also, because some other method, some other software, not TensorFlow, but there is PyTorch, there is Tiana, and so on. They use another algorithm. So there is another algorithm. I'll discuss that next time also. That's not very hard.